Okay, we'll continue talking about our definitions of acids and bases. In our last video, we had already talked about Arrhenius, right, where acids were substances that when we dissolved them in water increased the concentration of hydrogen ions, and bases were things that when we dissolve them in water increase the concentration of hydroxide ions. The problem with Arrhenius's definition, right, if we go back to Arrhenius, right, Arrhenius talked about acids and bases in separate solutions. Right? And, we knew that, the most common reaction was that, acids would react with bases to make a neutral solution, right? So there was a neutralization reaction that was fundamental. And the other thing that we knew, if we took very concentrated solutions of acids and bases, when we reacted them, we would get either solutions or substances that were identified as salts or ionic compounds. Right? Ionic compounds, and that these reactions were strongly exothermic. Right? That there were important reactions of acids and bases that were strongly exothermic. And so there were, Arrhenius's definition didn't adequately address for chemists the reaction between acids and bases that was so fundamental to their identity. And so we needed a good definition that could bring acids and bases together. So for this, we need some new people. Johannes Brysted, who was Danish, and Thomas Lowry, who was British. Right? And so Brysted and Lowry, who we give co-credit for, right, for this definition, looked at acids and bases in solution together and what was the nature of their interaction. And so independently, they made this proposal in about 1923, so about 40 years after Arrhenius had made his definition. And so what they said, they talked about their role in the role of acids and bases in reactions. And so to Brysted and Lowry, right, in talking about these, their participation in reaction, acids donate hydrogen ions to other species in reactions. Okay? So it's still focusing on hydrogen ion behavior, but here we're talking about hydrogen ions leaving the acid species and being accepted by something else, right? The hydrogen ions are passed from one thing to another. They're not just running around free in solution, right? And to Bronsted and Lowry, bases accept hydrogen ions from other, helps if you can write other, species in reactions. Right? And so acids and bases are two parts of a pair, right? So, right? Acids donate hydrogen ions to other species. Those species they donate to are the bases. Bases accept hydrogen ions from other species. Those species they're accepting hydrogen ions from are the acids. So acid behavior and base behavior has to be paired and go together. Let's look at a couple of examples. So in this first example, we've got nitric acid and we've got ammonia, right? And so note here, right, we've got no hydroxide ion, right? Bronsted and Lowry's definition didn't require that the hydroxide ion participate, but we'll talk here in a second about where it does. And so when these react, what we're going to get is, right, the nitrate ion right? Our nitrate ion plus the ammonium ion. And if we're in solution, those two ions will stay separate, right? So to Bronsted and Lowry's definition, this is an acid-base reaction because, right, there is a hydrogen ion, right, that's being removed from that spot and is appearing in that spot where there wasn't one before, right? And so to Bronsted and Lowry, the nitric acid, the thing we name as an acid, in this case was acting as an acid, and the ammonia then was acting as the base, right? It is the thing that accepted, right? Now, most acid-base reactions are reversible. Now, in this case, I used a strong acid example, and so this may not be the best place to introduce it, but I'm going to do it anyway. If we consider the possibility of a reverse reaction, right, then in order for the reverse reaction to occur, right, this hydrogen ion has to leave and go to this position where there isn't one. And so in the reverse direction, the ammonium ion would act as the acid and the nitrate ion would act as the base. So with the Bronsted-Lowry definition, we get a new concept in terms of the relationship between our reactants and our products. Our reactant acid, its remnants become a base on the product side. Our reactant base, its products become an acid on the product side. And so we call the relationship between those two, we call this the conjugate base and the conjugate acid. And so then we call, right? So we call nitric acid and its conjugate base, the nitrate ion, a conjugate acid base pair, right? And similarly, we would call ammonia and the ammonium ion a conjugate base acid pair, right? So we get this concept that for every acid there is a corresponding base. There has to be, for every acid, there has to be another base on the reactant side, because it takes an acid and a base to transfer that hydrogen ion, right? But also, for every acid, there is a base on the product side. And for every base, there's an acid on the product side. And so we get this concept of conjugate base, conjugate acid, and conjugate acid-base pairs. Let's talk about, the relationship between the Arrhenius definition and the Bronsted-Lowry definition, right? The Arrhenius definition, let's start with acids. The Arrhenius definition started with an acid in solution, and so let's use the one we've been using. Let's use Let's use. Stop it. Let's use nitric acid, right? So Arrhenius put that nitric acid in water, right? Water was the solvent. And so Arrhenius said that would dissociate to form hydrogen ions floating around with water molecules and separate nitrate ions floating around with water molecules, right? That's what Arrhenius said happened when you put an acid in water. If we take that same acid but consider it with Bronsted-Lowry language, right? Bronsted-Lowry suggested that we couldn't have an acid without a corresponding base. Well, the only things that are in there are nitric acid and water. So in the Bronsted-Lowry sense, it has to be water that's acting as the base, right? So just changing colors, right? So we're still going to have our nitric acid, but it has to react with something, and what it's going to react with is water. And there has to be a transfer of a hydrogen ion from one thing to another. And so if nitric acid is going to act as our acid and water is going to act as our base, water has to then be the thing that accepts the hydrogen ion. And so we're going to end up with this ion, right, plus the nitrate ion, both in water, right? And so this ion, we give a new name, the hydronium ion, right? So even in a simple acidic solution, right, of an acid in water, there's still, Bronsted and Lowry insist that we still have an acid and a base. And now on the product side, the hydronium ion becomes the conjugate acid of water, right? And then we have the nitrate ion as the conjugate base. And so we get the same result. And so we see this when we talk about acids and bases all the time. And you may have seen it depending on who taught you your first acid and base chemistry. Some people, when they talk about acids and bases, talk about hydrogen ions being aqueous. Others do the same problems using the hydronium ion. Whoever taught you that probably didn't realize it, but really all they're doing is, if you use hydrogen ion language, you're talking like Arrhenius. If you use hydronium ion language, you're talking like Bronsted and Lowry. It ends up that the math of the problems doesn't change, but really that becomes sort of this fundamental separation in the way basic chemistry is taught. Do you teach basic acid-base chemistry from an Arrhenius sense, or do you teach it from a Bronsted-Lowry sense? And what chemists have learned is they can go back and forth, and you will see me switch back and forth. I tend to do a lot of Arrhenius because it just makes writing the problems a little easier, right? There's a little less to write sometimes than if we do the Bronsted-Lowry. But for dealing with acids in water, it doesn't change the way we work the problems. Let's consider how Bronsted and Lowry might describe what's going on in a neutralization reaction. So say we have a solution of an acid like formic acid. Right? Here we have something like formic acid. And we're putting it, right? All of this is in water. And so we put it with sodium hydroxide. So we've got hydroxide ions plus sodium ions to participate in the reaction, right? And so the products then of the neutralization reaction would be the formate ion, right? Be clear here. Right? Water. And then the sodium ion would be unchanged, right? And so the sodium ion would be classified as a spectator, right? The acid, the formic acid would be the acid. The formate, it helps if you spell formate correctly. There's an R in formate, right? The formate would be the conjugate base. The hydroxide ion would be the base. And water would be the conjugate acid. Rewrite that to get it clear. So in a neutralization reaction, it is the hydroxide ion that acts as the base, right? And then what's left over, right, if we pair up the spectator ion, and in this case, the conjugate base anion, those, if we evaporated our solution, would leave behind an ionic compound that we call a salt. And so that's the basis of a neutralization reaction in the Bronsted-Lowry sense.